Okay, kia ora everyone. Tēnā koe and welcome to Café Scientifique, ko Scott Pilkington ahoa. I'm the current convener of the Auckland Café Scientifique series, and I'll be your MC and moderator for tonight. Those of you who have your videos on, if you can hear me, can you do a thumbs up? Fantastic. All right, so I'm going to assume, therefore, that everyone can hear me, and we'll get started. So before we begin the night's proceedings, I'll just run through a couple of announcements and some housekeeping matters. So the Auckland Café Scientifique series is part of a worldwide phenomenon, and it is brought to you by the Auckland Museum Institute, which is simultaneously part of the Auckland War Memorial Museum and also the Auckland branch of the Royal Society Te Aparangi. So at this stage, normally for a cafe, we would all be having something to eat and having something to drink from the bar, which we can't do tonight. I have myself a lovely glass of lemon tea, which will have to suffice me, and presumably you will have your own thing as well. Normally at this point we would run through some upcoming events other upcoming events that we have on, but at this stage we have no other upcoming events, so the section will be quite short. During this lockdown, the Auckland Museum is closed, but they do have a great online presence, which you can check out by going to www.aucklandmuseum.com. And one of the things that they do have there that you can download are some really cool Chrome desktop backgrounds and some Zoom backgrounds. I don't have, normally I would have some running, but for some reason today Zoom has decided that my face is the white part of the video and it was replacing me with the cool backdrop, so I've had to turn mine off. But there are some really cool ones that you can take a look at. Last time I looked, I think there was something like 196 Zoom backgrounds that you can download, so those are some great resources that you can look up on the Auckland Museum website. Now for some housekeeping. So for those who are new to the Café Scientifique series, a quick reminder of our format. So we normally have 15 to 20 minutes of presentation, then a short break, and then about an hour of question and discussion time. So working in this digital format that we're doing at the moment isn't easy. So we've changed some of the settings. So I've muted everyone's microphones except my own and JJ's, so you won't be able to talk to the speaker the way that you normally would. But what you can do is you can open up the chat function and in the everyone chat, put any questions and comments that you might have, and then I will go through, filter those a little bit, and pass those on to JJ to answer. I haven't been able to close the chat and screen share function for audience members. So if someone other than JJ or myself message you or share information with you, please send me a message, or there's a raise hand function in the chat. And so let me know and I'll block people who are inappropriately contacting you during through this format. So a couple of other reminders for those who are new to our series: please keep an open mind, be respectful towards our speaker and each other, and intolerance is not tolerated. Lastly, as we're not meeting in person, we can't pass the koha basket around. So if you would like to donate to the Auckland Museum Institute, please follow the instructions sent in Greta's email yesterday, or head onto the Auckland Museum website and click on the Donate Now button. We won't be circulating any links or bank account numbers or anything like that tonight during the session. So if someone sends you something, please just assume that that is spam and ignore the message. Now, last thing before we really get started is we haven't run an event like this before, so please bear with us a little bit. After the talk is finished, we'll be looking for some feedback on how all of this has gone. If you'd like to give us some feedback, just flick an email through to institute@aucklandmuseum.com. That is, again, institute@aucklandmuseum.com, and that will give us some idea of how you think that we're doing. So finally, tonight's talk is Exploding Binary Stars and Gender Binaries by Associate Professor JJ Eldridge, who is an astrophysicist and an Associate Professor at the Department of Physics at the University of Auckland. Over the past few years, there has been a change in our understanding of how important binary stars are in our universe. Whether from neutron star mergers, exploding white dwarfs, or core collapse supernovae, stellar explosions in binary systems are extremely important for creating the elements we depend on for life, like iron and oxygen. Dr. JJ Eldridge will discuss how different exploding binaries create different elements and how we can trace their creation back through the history of the universe, showing how we can link the rarity of the explosion to the rarity of the element. JJ will also share their experiences of being a transgender academic, both the good and the bad, and how we should explode the idea that gender is only a binary too. So please join with me as best you can in welcoming JJ to present tonight.
Thank you, Scott. I tried to unmute myself and then I realized that you were doing it. So yeah, but thank you, Scott, for the introduction, and thank you for inviting me, and tēnā koutou, tēnā koutou, tēnā koutou katoa, everyone. So I know I'm in an unusual position because normally you wouldn't have slides in a presentation during a Café Scientifique. So I know I'm quite lucky that I can actually share a screen. And so I've got a few slides because astronomy is a visual subject. But I'm a theoretician, so my pictures of stars are actually normally just a big group of numbers. So then I'm going to talk a bit about astronomy, and then I'm going to talk a bit about science fiction, because it's a good way of exploding gender binaries is actually to look at, I'll use a Star Trek example or two, to look at how, you know, we analyze gender in a different way. So let me see if I can share my screen, and hopefully some of you can still see this. And I'm just going to move you up here because then I can see. So I'll keep an eye on the chat window in case none of you can hear me. I'm going to assume you all can hear me. And if you're wondering what this is just a diagram that's been made to look fancy that we'll come to later because it's trying to illustrate the complexity of how binary stars evolve. That's right. So Scott's already introduced me. I'm Dr. JJ or Jan Eldridge. I don't mind using either. My pronouns are she, her, or them, they. I'm an astrophysicist, so while I do astronomy and look up, I really am thinking about physics. I'm trying to do physics with stars because there's a lot of things we can do in stars that we can't really do in the laboratory. And yeah, my tagline is I study exploding binary stars while exploding that myth of a gender binary. And I work on lots. I work on stars, galaxies, supernova, gravitational wave events. With what I did when I was doing my PhD, I was making computer models of stars. And it turns out when you look at the universe, most of the things in the universe that we can see are actually based on stars. So it turns out I end up having to try and work out how to observe my computer models of stars in the same way that an astronomer, an observational astronomer, will look at stars in the universe. I'm also on Twitter on astro_JJE. Why do I do astrophysics? I love putting this slide in because I think it's important. And basically, I watched too much science fiction, if there is such a thing as too much science fiction, when I was younger. So when I was growing up, Sylvester McCoy was the Doctor. I kind of started watching when it was Colin Baker, but I was too young, and so Sylvester McCoy was my first Doctor, who I really enjoyed. And of course, you know, we all love Doctor Who now, there's so many episodes. But when I was growing up, the UK History, what was it, UK History? UK Gold channel, TV Gold channel, would actually have all the old episodes of Doctor Who on. So I used to watch all the old episodes, especially the Tom Baker and the Peter Davison ones. And so, you know, even though I was growing up and even though Sylvester McCoy was my Doctor, I still got to see all these old episodes, and I still have quite a collection of DVDs today that I love looking through. And I've recently got to write a book chapter on Doctor Who, or science in Doctor Who, that's going to be coming out sometime towards, I think, next year. So, you know, Doctor Who got to travel all around the universe, teaching young people about the universe and trying to make the world, the universe, a nicer place. And being an astronomer is kind of the closest I can get to that, because I get to explore the universe, understand how it works, but I also have to lecture and teach. And so that's a really important part of why I enjoy my career, is because, you know, I get to go and teach young people about how exciting the universe can be, as well as trying to make the universe a nice place. Well, Earth at least, although, you know, it's difficult. The other good thing about this is you'll see later that you can use cases of science fiction to teach things. So, for example, you know, you can look at the extrasolar planets we have around the universe, And we can say, when we look in science fiction, do the planets we see in science fiction actually represent what we see in the universe? Because we know now, you know, we can look at the physics of things like WALL-E, Star Wars and Star Trek. How realistic, what do the movies and the TV series get wrong? But also, yes, you can look at mind and body swapping and gender diversity within science fiction. So that's another reason I love, because it's a good way, because we all like science fiction movies. Well, many people like science fiction movies. And it's a way of asking what if and how can things work. But okay, let's go back and come back to thinking about single stars and binary stars. And, you know, so main topic of my talk is binary stars. So what is a binary star? Well, let's get there in a second, but first of all, let's ask, what's a single star? And when we look at our sun, it's very easy to forget the sun is just actually quite a boring, ordinary star. It's just very close up, which means that other stars are other suns, but just very far away. And our sun is on its own. It's not got another star going around it. It's got Jupiter, which is about 100 or 1,000 times too small to be a star. But if it was bigger, then you would have a binary star system. You'd have two stars orbiting around each other. In some ways, you can think about the Earth-Moon being a binary planet, because you have the Earth and the Moon orbiting around each other. So a binary star would be the same. So the sun is quite boring in some sense, and single stars are quite boring because they've only got one life story, one way they can go from their birth to their death. So this is what the schematic shows. Hopefully you can see my mouse pointer here. If you look at the blue dots, you can see that's what I would represent as a main sequence star, like our sun, where it's burning hydrogen to helium in the core. So it's getting energy from nuclear fusion, making heavier elements out of, lighter elements. Eventually it uses up all the hydrogen fuel in its core, and so it becomes a helium core, which I've illustrated in green here. But then the envelope, the stuff that isn't burnt, stays outside that in an envelope, which actually ends up, the star gets as big as the solar system. It can get up to thousands of times the sun's current radius, and the sun itself is already 100 times bigger than the Earth. But in massive stars, so in our sun, it will go a little bit further, and the helium in the core will carry on burning, and you'll get carbon and oxygen being formed in the core. So you end up with something about the mass of the sun's worth of carbon and oxygen in the core, and then you'll have this helium mantle around it. And our sun will stop there. It will lose all the hydrogen on the surface, and then this core will be exposed, and it will become a star, type of star called a white dwarf, which ends up being about the mass of the sun, but something about the size of the Earth. So it's a very small, dense star, and it will just slowly cool away over the age of the universe. More massive stars, the ones I really enjoy studying, about 8 times the mass of the sun and above, don't stop once they've formed carbon and oxygen. They can go further, all the way sometimes up to the iron, cobalt and nickel elements, which are the most stable in the universe. And of course, when you get to that point, you can't get any more energy out. If they're the most stable, if you try and squeeze 2 iron atoms together, you have to put energy in to make new elements. And so there the star would actually explode, which normally I would show this as a big bang here, but I wanted to keep the talk short. And you get a neutron star or a black hole that comes out. And so that's something about 1.5 times the mass of the sun, but something only the size of maybe 10 kilometers across. So something the size of Auckland city. And so it's incredibly dense material. And of course, a black hole is even denser still, being something like 3 times the mass of the sun, but only 2 kilometers across, which you can walk in about 20 minutes. So that's how stars shine, and that's basically always what happens. A star always becomes this red giant, and the only difference between how far it goes is how massive it is. And that's the same story for any massive star. And it gets quite boring, really. But when you try and put another star in a binary with the main sequence star, so here's one main sequence star, and I put another star next to it, and suddenly things get complicated, because you've not just got to worry about the mass of that star. Is it going to go supernova? Is it going to form a white dwarf? You have to worry about the mass of the other star, and also how close is it? How close it is. If it's very far away, then nothing's going to change. The star will still evolve as a single star. But if it's close enough that when this star becomes a red giant, the other one is touching it, then we get a problem, because the stars can get in each other's way. And of course, it's going to vary what happens depending on whether it's very close, and so it interacts sooner, or if it's further away. So if it interacts nearly towards the end of its lifetime to when the star is getting as big as it could be, which is kind of what all these arrows are trying to show. So I'm not going to go down each one of these pathways, but you can see suddenly for single stars, we have that one direct line. And here we basically have anything goes almost. You know, the stars can merge together and they can form a superstar that's rapidly rotating. Or more commonly, you can actually take off the hydrogen envelope and you get the helium core exposed. And we know this happens because when we look at supernovae, we see some with hydrogen in and some with no hydrogen in, which at a basic level tells us that, you know, that wasn't in the star. So there are some stars that explode in supernovae that have lost the hydrogen on their surface. And we think, while single stars can maybe do that, binary interactions tend to really push that a lot more. Now, just trying to remember where I've got to go with this. One thing that can happen, of course, is that if you have one star go supernova, you can form a black hole or a neutron star. Most of the time, actually, the two stars fly apart after the first supernovae, but sometimes they stay bound. So then you have a black hole or a neutron star going around another star. And we see these things because, you know, if you've got a black hole next to another star and that gets too big, then you see the black hole feeds off this other star. But then that one can explode and you can get two black holes together. And now over the last few years, we've been able to start detecting these black holes and neutron stars actually spiraling in together and merging just because of gravitational radiation, which is an effective general relativity. And so actually we're starting to measure the endpoints, the very endpoints of the binary by these like very sensitive instruments we have. But that's not the story I'm going to tell. You can always ask me about that. You can ask JJ, Jan, what is a gravitational wave event? But what I'm going to talk about now is another type of, or talking about where we come from. So this is all wonderful. Stars evolve and they explode in different ways. But what does that have to do with us? Well, it has to do with this really nice plot that's made by Jennifer Johnson. And apparently she made it because someone was wrong on the internet. And so she made this plot, and there's many different versions of it out there. I really like this one. There's some others that you can find on Wikipedia and other places that are also quite nice. But it tells you, this is the periodic table, and it's got all the elements that we know of in the universe. So if I was watching Iron Man 2 the other day and they create a new element, and it's one of those moments as a physicist you look and you go like, but you can't do that. No, sorry, I'll keep on track. All the elements in the universe, and so you can see hydrogen and helium up here on the top left and the top right were formed at the beginning of the universe. So, you know, you've got hydrogen in your body. It's probably the most numerous element by number in your body because it's in water, and you're made of a little bit of exploding universe. But you also need carbon and nitrogen in your proteins to be able to live. You also need oxygen to be able to breathe, and you need iron to be able to carry the oxygen around your body. So this is cool because if you actually do what most people can do now, you can look at the color. So the oxygen is this nice pale green color, and it comes from exploding massive stars. So all the supernovae I just told you about, those that are about the stars that are 8 times the mass of the sun and above, get to the end of their lives. When they explode, they're producing all the oxygen that you're breathing right now. They're producing all the oxygen that's in your water. That's kind of exciting because it means we need stardust to live and also to drink. And that's like amazing. But if you then go on to think about iron, now there's a problem with massive stars. They do make some iron, but not enough because most of the iron goes into the neutron star or the black hole. It doesn't produce a lot. So there's something else that comes here, which is exploding white dwarfs. And now you're saying, but JJ, you said that the sun produces a white dwarf. So how does a white dwarf explode? Unfortunately, our sun will never explode when it comes to a white dwarf. Our sun will only explode if it's in a binary system with another star, because a white dwarf has a maximum mass, and it gets to that mass, it'll explode. And so we need stars like our sun in binaries over the age of the universe to produce iron so we can have hemoglobin in our blood to carry the blood around, right? And this will be the same story if you even thought about like having copper in our blood, like some crabs do, or volcans, right? They have green blood because they've got copper rather than hemoglobin rather than iron in their element, in their chemical formula, in the molecule that carries oxygen around their bodies. And so we need these two types of stars, right? We need to have exploding white dwarfs coming from stars like our sun in binaries to produce iron to live, but we also need those massive stars. We also need dying low mass stars, for those of you who are keen, and you're going to say, but we need the carbon and nitrogen come from these. So that is stars like our sun towards the end of our life, towards the end of their lives. But there's something interesting here, and this is something I've been doing recently. We can do better than just saying, oh, we need these stars, these elements. We can trace how much of the different elements was made at different times in the universe. So one interesting fact is that massive stars, the more mass they are, the quicker they evolve. And so stars like our sun have a 10 billion year lifetime. Massive stars that explode in supernovae have millions of years lifetime. So that's a big difference, like thousands, on order of thousands of difference between the lifetime of these massive stars that explode and the white dwarfs that explode. So we can trace that back through history. And with my computer models, what I've been able to do is, from observations, which are these crosses, you can see if we're going back in redshift, which is effectively back in time, maybe over 10 billion years into the history of the universe, the peak of the core collapse supernovae is quite close to about 10 billion years ago. So you can actually see more of these core collapse supernovae. The universe became very oxygen rich very quickly. So it would be great, we'd be able to breathe. But here, this green line, which is underneath this red line, if you're colorblind, I've just realized that's terrible. I apologize. I will change that next time I give this talk. This curve is the exploding white dwarfs that produce all the iron in the universe that we need to carry the oxygen around our bodies to live. And that peak is actually more recent. That's only a few billion years ago. And so you've got this thing that we can now study how things have changed in the universe. And we can actually start to understand habitability of the universe, not just like how nasty is the universe, how many supernovae might explode nearby and kill us, but when was the chemical composition correct that we could actually evolve and like live, right? Because you've got the elements that went into our solar system were locked in about 5 billion years ago when the sun was formed, which is round about here. So we're lucky that our solar system would have formed quite close to the peak in iron, because otherwise, you know, we wouldn't have so much iron in the planet, although it's not the most common element. So yeah, if you're wondering what long gamma ray bursts are, they're a separate type of thing and a separate type of explosion, because we can look at all these different explosions. But I just wanted to make that point that, you know, we're looking at this periodic table, that's all the elements we need to live. And that's kind of interesting, because it means we can now not just look at what element comes from these, but we can track how the amount of different elements have changed through the universe, which also tells us something about stellar evolution. Anyway, okay, so that's my stars bit. I'm just going to try and take a break. I know I'm probably going a bit too long, but I'll take an extra 5 minutes just to talk about some science fiction about gender binaries. So one of the best slides I like showing, if you want to try and understand humans, right? Because I've just gone on about the universe, I've gone on about stars, and everyone gets fascinated because, you know, stars are pretty exciting. You know, they explode, that's pretty exciting too, and they're extremely complicated. And everyone seems to accept that space and the universe is complicated, and it is, because it's hard to work out how things all work together. Otherwise, if it wasn't, physicists would be out of a job because we would know everything. Turns out people are complex too. And, you know, we sometimes forget that. And we think about, as you remember when I was talking about binary stars, there's a range of behavior because it depends on the mass ratio of the two stars, how massive they are, and how far apart they are. So it gets very complicated. People are similar too. And so we have these things here. This is the genderbread person from the website. There's a few different versions of this around. But it's just trying to break down this idea that people are not a binary, right? You're not a man, a woman. You're not left-handed or right-handed. Some people can be ambidextrous. It's that kind of thing, that everything is a range. You're an n-dimensional space, right? We're all inherently complex, and some people vary in other ways that people don't. And one of the problems is, you know, you've got to try and understand, listen to everybody to try and understand the sheer complexity of possible variation. And this is just trying to break down things into gender identity, gender expression, which your gender identity is who you are, your gender expression is how you like to present. Your biological sex is basically judged by a doctor when you're born based on your reproductive capability. And your sexual attraction, your romantic attraction are completely different things as well. They're way off the bottom. And all of these things don't have to be related, right? So I'm transgender, which means my gender identity does not link in what people would assume to my biological sex, right? So because I'm a woman, a trans woman, whereas I was assigned male at birth. So that makes me transgender. And my expression changes from time. I mean, that happens for everybody, even if you're cisgender, which means, you know, you are linked male to man, female to woman. Everyone's gender expression does change with time. So, you know, you can think of many examples of this, that you know people who don't necessarily fit into what we would term the stereotypical or the gender conforming person. So that's just trying to make the point that people are complex. But I'm just going to use science fiction now to do a few case studies and to make you think about things in an interesting way. So these are all Star Trek examples. I apologize. I have a longer talk, which I need to rewrite, because every time I give this talk, people go like, JJ, you need to read this book or watch this TV series. And there's so many now that I have to redo the entire thing. And I avoided it because it's going to take too long. One example, if you want to understand what it's like to be trans or even non-binary, somebody who's outside the male-female gender binary, is a series episode called The Outcast, when there's this androgynous species, the Janai, who have evolved beyond gender, which would be great, right? Everyone's genderless and it's the same gender. And Riker has a relationship with a character called Soren, because she's a woman. We know this is true, right? Because in the Janai, it was like 96% or something of people are genderless and happy, but a few percent feel that's wrong and they want to put themselves in the binary. So this is kind of a reverse of what we know in society today, where we know 95–96% of people are what we term cisgender, their biological sex and their gender identity match, whereas a few percent of people don't quite fit into that, both transgender and non-binary people. And so maybe if you wanted to understand what it's like to be trans or non-binary, imagine yourself in a society where everyone's genderless and you know you have a gender, right? And so this is actually a really nice analogy, because it's just flipping the population around, right? And that would be pretty unpleasant unless people just said, hey, that's okay, just be who you are, which would be good enough. It's interesting when you look at this and you read up about the episode that Jonathan Frakes, who plays Riker, thought that the episode should have been more daring, and that, you know, it should have been played by a male actor rather than a woman, which would have been interesting. There's other things that come up when you're looking at different species. And there's one really interesting species called the Trill. Sorry, I was going to talk about them in Stargate, which is the Torquera and the, I've forgotten. Somebody will tell me in the chat later. But this is a species where you have a symbiote that goes from host to host. And so the symbiote has no gender, but of course it inhabits a body of a person who has a gender. And so, you know, the first time the symbiote goes into a host, it absorbs the gender of that person. But as it goes through all the different hosts, what happens and how does the host pick up from the symbiote all its different gendered experience? And so this was first shown in an episode of Star Trek Next Generation, where there was a character who Beverly Crusher had fell in love with, had an accident, symbiote had to go into Will Riker, and so they carried on pursuing their relationship. When the new host turned up from Trill, it was a woman. And at that time, Beverly wasn't right, and of course Star Trek Next Generation didn't feel it was right to, like, that was a problem for the relationship, which is fair enough. But then it's interesting when you then come back to years later in Deep Space Nine, which is, to be controversial, one of my favorites, although I prefer Voyager. Well, it's difficult to judge. Anyway, Jadzia Dax is another Trill, and she's in the entire series. And she does change host once towards the end. Sorry if I've just spoiled that. But she meets another Trill in so it's the same symbiote that she was married to in the same host, but now it's the same symbiote in Dax, Jadzia Dax, compared to but with a different host. But the relationship basically starts off again, and they have to decide if they wanted to be ostracized from Trill society or not, which is interesting. And it's a really wonderful episode because it's just two people in love. And of course, in the end, they decide to basically not pick up their relationship, and which is sad, but also it means they still get to contribute to Trill society. But also in Deep Space Nine, there's the best example of how to be nice to a trans person. So, I mean, Klingons get trans rights, because here's Jadzia Dax meeting Kor, her Klingon friend, who used to know the previous host, who was Curzon Dax, who was a man. Of course, they would get on great. And so Dax goes, how about just a great big hug? And Kor goes, Curzon, my beloved old friend, right? So gets it wrong, misgenders her, and dead names her. And then Dax goes, I'm Jadzia now, takes on advice. And the Klingon now goes, oh, well, Jadzia, my beloved old friend. So, you know, if Klingons can understand being nice to trans people, everyone can do. And it's a quite funny episode anyway. Anyway, and just to finish off this talk, I just wanted to say, you know, this is it would not talk about being transgender and gender diversity without mentioning Doctor Who and their recent change, right? Because you can now, whenever you're talking about Doctor Who in general, you have to say they. If you're talking about specific Doctor, that's when you use he or she. It gets complicated, but I've been told this by the person who was the editor for the book on Doctor Who I had to write a chapter for. And if you want to have another insight into what it's like to being transgender, it's like when the Doctor Who regenerates. Each time, that's like being a new person. And it's quite nice, this phrase I've outlined in bold, which is right now I'm a stranger to myself. There's echoes of who I was and a sort of call towards who I am. And I have to hold my nerve and trust all these new instincts and shape myself towards them. I'll be fine in the end, hopefully. And then she goes on because she needs to save people, and that's what the Doctor does. And it is that kind of like, it's strange that when you're trying to redefine yourself and be a new person, that, you know, you still have to try and think where this call is and try and work out who you want to be. And I'm sometimes still much in that. And so I will freely admit, I don't know who I am still. But, you know, I still try and be good and try and study and understand the universe. Anyway, I hope all of that was interesting. Probably an information blast. I probably spoke too quickly. I'm going to go back on and see who's still left here, and everyone will probably have left, but we'll see. And I hope you'll have some interesting questions to ask. So I'll stop sharing now. And hang, where's my mouse gone? I've lost my mouse. No, there we go. And if anyone wants to have another look at any of the slides, you can certainly ask questions. So yeah, thank you very much for listening, everyone.
All right, if we can just have a little round of applause for JJ for such a great talk. I think that just about makes us for tonight. I'll just quickly turn on the screen share again for everyone so you can just see if you want to. Oh yeah, thank you, Bob. If everyone can just give a quick round of applause. Again, thank you so much to JJ.
You're welcome.
And I've just popped up on your screen. Hopefully everyone can see it. If you want to follow JJ and see all of the amazing research that's being done, head over to Twitter. If you want to contact me about things, if you desperately would love to host to give a talk in a future Café Scientifique, I would love to hear from you. Hit me up on Twitter, or you can email institute@aucklandmuseum.com, and they'll pass that on to me. I'll just mention I don't work at Auckland Museum, but Greta, who maintains their email address, passes all the feedback on. If you've got feedback about how tonight's cafe went or anything like that, check out, flick an email through to institute@aucklandmuseum.com, and we'll get on to that. I'd just like to thank all of you at home who have tuned in and given up part of your Wednesday night to join us. Thank you so much for coming, and thank you so much for all of your amazing questions. I myself will in a few minutes be going off to watch some more Marvel films, because we're at home at the moment. We are working our way through the Marvel films in the order that they're set rather than the order they came out, and so tonight's one is Civil War, where our favorite scene is where Spider-Man questions the physics of the fighting and says, hang on, this shouldn't be possible. How does this work? That shouldn't bounce like that. So it is our sort of favorite film for that, for actually questioning how ridiculous some of the science is in the Marvel universe. So thank you everyone once again, and at this stage we haven't arranged the next cafe, but once we have that sorted, we will send a message out to everyone, same place, same time, in a month or two. Thank you so much all again, and have a great night.
Thank you, everyone. Thank you, Scott. Bye.